Hello guys, welcome back. Today we're going to be learning about drag on a wing. Now drag on a wing is very similar to drag on airfoil that we talked about in the previous video. However, we have to consider this one more additional drag, which is called the induced drag. Now if we look at the back of the airplane, let me draw this airplane that we're looking at from the back. On the bottom of the wing, we have higher pressure compared to the top of the wing, which has lower pressure because the airflow moves faster on the top of the wing compared to the bottom of the wing. So on the bottom of the wing, we have high P, and on the top of the wing, we have low P. And as we all know, pressure likes to move from high pressure to low pressure. So there's only one way for this air to move, but they want to move from the bottom of the wing to the top of the wing, and this causes a vortex. On the left side of the wing we have a clockwise vortex, and on the right side of the wing we have the counterclockwise vortex, and the net effect is a downward airflow. This downward airflow actually affects the entire region of the wing, and this we have a, professional word, and we call this the downwash. So how does downwash affect the airplane? Okay guys, so let's assume the airplane is flying at a certain kind of angle of attack, and we're gonna say that's the total angle of attack, and we're gonna denote it as alpha in the subscript total. However, what the downwash does is that it actually decreases this total angle of attack. Well, how does it decrease it? Well, we have V infinity, which is how fast the airplane is moving, and we have the downwash, which is denoted as W, and this angle right here is the induced angle of attack, and the induced angle of attack is subtracted from the total angle of attack. Yeah, I'm gonna try to do my best to draw a straight line here. Maybe I should use a different color, probably green, and then I'm going to use the straight line program right here, then do that. If they want, they don't like this, huh? Okay, now we have it. Okay, so here, this angle, now this is very exaggerated, but this is the induced angle of attack. So what's our real total angle of attack? Well, it's right here, and we will probably have to use a different color as well, just to emphasize the difference. And this here, we actually denote it as the effective angle of attack, and this is what is important. Total minus the induced angle of attack. So as we all know, lift is proportional to the angle of attack, and this sign is the proportional. So the greater the angle of attack, the greater the lift. The lower the angle of attack, the lower the lift. Now, how does the induced angle of attack affect our lift? Well, the greater the downwash, the greater the induced angle of attack, and the smaller the effective angle of attack, which reduces our lift because our effective angle of attack is reduced. There is an analytical way of expressing induced drag, and that is denoted as CDI equals to CL squared over pi EAR. As we all know, CL is the lift coefficient, pi is simply 3.14, and E is actually something that we saw is like the new thing that we're seeing today, which is called the span efficiency factor. And usually this is 1 over 1 plus delta, and this usually varies from 0.95 to 1.0. How about AR? Well, AR is actually the aspect ratio, and aspect ratio is a very important characteristics that in aerospace engineering. This is usually B squared over S. B is the span of the wing, S is the area of the wing. So how can we reduce the induced drag? Well, there are two ways. Number one, make span efficiency factor as close to 1. Now, usually, well, always, E does not exceed 1. 1 is the maximum. And the worse the wing is, the value of E decreases, but usually it doesn't go down below 0.95. The second way of reducing the induced drag is increasing AR. So let's talk about these two methods. Which one is better and why? Okie dokie, so let's talk about the first option, which is to make E, which is the span efficiency factor, as close to 1. Is that a really good method? I don't think so, because as we talked about it, the worst it can probably go is 0. Okay, what is wrong with my pen? 0.95. And the best it can go is 1. And this is actually the elliptical wing. Elliptical wing has a very nice lift distribution, which makes its span efficiency factor 1, or very, very close to 1. But obviously 0.95 and 1, there's not a big difference. The only difference is 0.05. So this is probably not something we should focus on when we're trying to reduce the induced drag. So should we focus on increasing the aspect ratio? Well, let's see. Number 2, increase the aspect ratio. Arrow up, AR. Now, let's assume that the area of the wing will be 50 meters squared. And we're going to make two different kinds of wings. The first one, very slender, thin but long. We're going to make it this 5 meters and probably this as 10 meters and this as 5 meters. I know this is not drawn to scale. And the other one, probably a little more stubbier, a little more squarish. And let's assume that this span is, okay, obviously this is not drawn to span. Maybe I should draw it to span it. Let's see, maybe something like this. And we can probably do like the opposite, 5 and 10, okay? What is the aspect ratio of this wing? Well, as we know, aspect ratio is span squared over area. Span squared, 10 squared, that's 100, over area, 50. Our aspect ratio is 2. It's really not good aspect ratio. Usually airplanes have, 6, 7, 8, 9. But this one, obviously we're using it to compare how aspect ratio affects the induced drag, right? So it doesn't matter. Over here we have a very unrealistic aspect ratio of b squared is 5 squared over, which is 25 over 50. We have an aspect ratio of 1 over 2. Unprecedented, probably. Okay, let's rewrite our equation for the induced drag. That is CL squared over pi EAR. Wow. Compared to the change in the span efficiency factor of 0.05, in the aspect ratio, we already have a difference of 3 over 2, 1.5. We have a difference of 1.5. So that's a lot better than changing the span efficiency factor, right? So if we assume, let's just assume that CL squared over pi E is, I don't know, let's say like, let's just say 5, okay? 5 times 1 over AR. Okay? Now, if we put this AR of 2, if we put 2, this will be 5 over 2. I'm going to change the color so we know what number we're using. So for this wing, we have the induced drag of 5 over 2. How about this AR, 1 over 2? If we put that in, this is going to be 5 times 1 over 1 over 1 over 2, which is 10. Wow. I mean, look at that. the induced drag for this thin, slender wing is 5/2. And for this really stubby wing, we have a induced drag of 10. So, as we all know, or as we can all see, the aspect ratio is very, very, very important for reducing the induced drag. So I think we are at the end of our tutorial. The drag on the wing, it's kind of the same as drag on an airfoil. It's friction plus pressure drag. But in that pressure drag, we have the induced drag. Induced drag is usually noted as the pressure drag. Okay, so that is all for today, and I will see you guys in the next video.